Hey folks, today we are going to build this plugin from scratch using modern C++ and the Juice framework in this free course. Check the description for links to the repository and to download the final build. Okay, what is this thing? This is the little brother of this other plugin, which is my new course for PFM C++ for musicians, which is where you can build this other plugin, which is also where you can learn modern C++ and the Juice framework from scratch, taught from the context of writing audio software in a mentored environment. You're not following videos, you're not watching someone else code, and you're not copying them. You're coding it yourself, and I'm reviewing your work. All right, enough about those. Let's learn about what we are going to build today. This is a 3-band equalizer with a spectrum analyzer at the top. It has a low-cut band, it has a high-cut band, and it has a parametric band in the middle. The low-cut band lets you cut out all of the low end of the signal. You can also control the steepness of the cut. The high-cut band lets you remove all of the high frequencies, and you can also control how steep that cut is. The parametric band lets you add notches or boosts, and we can also control how wide or how narrow those boosts are, and we can control the frequency. Everybody's familiar with this type of swept frequency sound. Above that, there are bypass buttons, which allow you to disable individual bands, which is always helpful when you're working on audio. Then above that is the response curve, which gives us a visual representation of what the filters are doing. Then behind that is the spectrum analyzer, and this shows us what we are hearing. And these always use a bunch of CPUs, so there's a bypass button for that as well. We're going to learn all the DSP that's going on in the background that makes this thing work. We're going to learn how to draw everything, how to draw the sliders, the bypass buttons, how to draw the response curve and make it respond whenever we adjust the sliders, and how to draw the spectrum analyzer. Okay, that's the feature set for this plugin and for this free course. My name is Chuck. I go by the name MattCatMusic on YouTube and Instagram. Once again, check the description for links to the repository and to download the final build of this plugin. So let's get started and write some audio software using modern C++ and the Juice framework from scratch. All right, the first thing we need to do is get set up with the Juice framework. Now, if you've never done any audio programming before, fear not. The only things you need are two tools, the Juice framework and then an IDE to write code in. That could be Xcode or it could be Visual Studio. It depends on what operating system you're running. I'm on Mac, so I'm going to be using Xcode for this video. If you've never set yourself up with an IDE before, I have 2 videos linked in the description. They take you through the process of setting up your computer with an IDE, getting the Juice framework, setting up Producer, setting up a Git repository, making your first project, and then pushing changes to that. And it basically gets you familiar with the flow, with the workflow that goes in with being a software developer in the context of writing audio software. Okay, so the first thing we're going to do is go get the Juice framework. So let's do that right now. I'm going to open up Safari, because that's this is like just a blank OS install. And I'm going to install, going to grab Juice. So Juice framework, just going to search for it. It is hosted on GitHub. So I'm going to go grab it here. Now what I'm going to do is I'm going to clone the repository. And the reason is because this is an active repository. They make a lot of changes to it, okay? So especially on the develop branch, we want to make sure that we have all of these changes because stuff's getting fixed all the time. Features are being added, that sort of thing. So if I have the repository cloned, I'm able to pull in those changes. This is different from if I had just downloaded a zip file. So that's why I'm going to do that. Okay, I'm going to go to terminal. If you don't have terminal open, just, terminal, open it like that, or open some kind of command prompt shell. Okay, then I'm going to, let's see, I've got my users folder right here, and I'm just going to clone the repository right into that. So git clone, and then the URL. Just like that. That's going to make the Juice folder, and it's going to download this repository into this folder, and it's going to include all of the commit changes as well. So let's just wait for this to finish. All right, there it goes. There's the Juice framework. Now, what we want to do is switch to the develop branch because, as I had shown, it is it contains more recent changes than the other branch. You can see that the develop branch is 19 commits ahead of the master branch. So to do that, we need to type in terminal. First, we need to go into the juice folder. So let's do that right now. cd juice /juice. And now we need to do git checkout develop, like that. All right, switch to a new branch, develop. Okay, cool. Now, I prefer to use a git GUI, so I'm going to be using fork from now on in the course of this SimpleEQ that we will be building. So I'm going to open that now so we can see what this repository looks like in that sense. So I'm going to open up fork. Fork is available from fork.dev. Okay, so here is the repository. I had already added it previously. And you can see here's all the commits that have been added and all the basically all the work that they've been doing on it. And you can see how frequently they update the develop branch. Okay, our next job is to open up Producer and use Producer to make a project. Producer is found in the extras folder inside Producer. Now inside here, you're going to find a builds folder, and in there is a project file for each operating system. You got Linux, you got Mac, and you got Windows. So if you're on Windows, open the solution file, depending on which version of Visual Studio you're running. If you're on Mac, you're going to open up the Xcode file. If you're on Linux, there's a make file, and you Linux users know what to do with make files. So I'm not going to talk about that. Okay, I'm going to open up Producer, the solution file. That's going to open up Xcode. And now all I need to do is just build and run. Okay, so we just need to wait for this to happen. Apologies if I start speaking fast. I like doing this stuff a lot, and when I get excited, I start to speak really fast. So if I happen to speak too fast, I'm probably going to take a step back and repeat what I say slower. So just apologies in advance if I start speaking really, really fast. All right, so let's wait for this to finish building. Build succeeded. Now it's going to run it, and then we will be able to configure this stuff. All right, so let's get this set up. Okay, we are presented with the new project wizard. Before we do that, we want to go to Producer and we want to configure our global paths. And these need to point to the juice folder and the modules folder. Now the juice folder, by default, if you clone the repository to your users folder, this stuff is going to be set automatically. It's going to go right to your users folder and then a juice thing. However, if you decide to put it somewhere else, you need to customize these modules. So click on this button right here, and then navigate to wherever your juice folder is stored for setting the path to juice. Then do the same thing for the modules. Click that button, navigate to your juice folder, and then navigate to the modules button, to the modules folder inside of that. Okay, and then if you rescan, it'll tell you if there's any issues or not. Once that is done, now you can go to the plugin right here, basic, and we're going to create a project called SimpleEQ. And then we can do create project, and it's going to ask me, where do I want to save this? Create project. I want to save it to this programming folder. And there it goes. It's going to save it. It's going to make it. And now if I reveal in Finder, here is my project. So I am going to make a Git repository next before I actually take a look around at the code, because it's always important to set yourself up with the Git repository in case you have to backtrack and undo some stuff or whatnot. So I'm going to do that next. All right, so in the interest of keeping everything neutral, I will not be creating the repository in fork, but I will be doing it in terminal because everybody's computer has a shell. It may not have fork in it. So what I need to do is first navigate to the folder that my repository is in. So I'm going to do that. CD, I'm just going to drag this folder in here. Now I'm inside that folder, and now I'm going to do git init, like that. Okay. Now I'm not seeing it, so I'm going to turn on hidden files. And now here is my Git repository. Okay. So what I need to do next is create a, I need to do an initial commit and commit the state of this. Now I do not want to include everything that's in this builds folder, and I do not want to include everything that's in this juice library folder, because juice library code folder, because every time we resave this producer file, it recreates these folders. The only thing we want to keep is the juicer file and the source file. So I'm going to add a git init file first, or a git ignore file, sorry. So I will do touch.git.gitignore, like that. That creates a document which I can open with a text editor and specify that I want to exclude this builds folder and this juice library code. So let me go do that. I'm going to open this with, I can open it with text edit. That's fine. And I want to write / builds with caps / juice, library code. Okay, that's the name of these two folders. And then because this is OSX, I'm going to do //.ds_store like that. We're not seeing any of those files right now, but sometimes we will. That's basically if I configure how this folder looks, it's going to get stored as a DS store file. And those are super annoying to include in your repository, so it's very good to keep them excluded. Okay, next I'm going to do git, git commit -m. This is my initial commit. Let's do a git status first. Let's see what we got. Git status. We can see that there are no tracked files, so let's add our files. Git add. And you'll notice that it's the untracked files does not include anything in the builds folder and the juice library code folder. And that's because of the git ignore file. It's doing its job. Let me just move this out of here so you can see what I'm talking about. So if I do that again, let's see. Let's do git status. We can see we've got these new files here, but it's also not tracking these guys. So there is a DS store somewhere. There's a builds folder and there's a juice library code. Okay, as I said before, we don't want those included, so I'm going to put that back. And then we'll do git status one more time. Okay, so we've got our git ignore, the juicer file, and then the 4 source code files. All right, now that we have those ready to be committed, let's make a commit. Git commit -m initial commit. Whoops, I forgot the closing quote. All right, that's fine. Good enough. Okay, now I can open this in fork. I can do file, open repository. So now I can actually see what's going on. And here's my initial commit. All right, good times. Okay, so if we want, we can go make a repository on GitHub and push the code there, or just keep it local. But either way, now we can keep track of everything. Okay, so I'm going to give you a quick overview of where everything happens in the source code now, before we actually start work on this. Okay, so this is going to be a brief overview of how these plugins work and where we will primarily be spending most of our time doing edits in the code. So we have 4 source files right here. We've got pluginprocessor.cpp, pluginprocessor.h, plugineditor.cpp, and plugineditor.h. Let me pull up the assistant editor so that we can see what's going on both sides. Okay, pluginprocessor.h. In a Juice plugin, you've got 2 main functions that are the most important. There's your prepare to play function, and then there is your process block function. Prepare to play gets called by the host when it's about to start playback. And then process block is actually what happens whenever you hit the play button in the transport control. When you hit that play button, the host just starts sending buffers at a regular rate into your plugin, and it's your plugin's job to give it back any finished audio that it is done processing. You cannot interrupt that chain of events. If you add latency or whatever, it can cause clicks and pops in your speakers, and that has the potential to damage speakers as well as explode eardrums. Just imagine this scenario that you're at a club and the sound system is super loud and your plugin causes a pop or a glitch, and the sound engineer or the DJ or whatever has their thing totally cranked, and there's just this huge pop and everybody's ears just go psh, like that. So that's why, that's the big thing about audio processing is you can't interrupt this process block and anything that goes on inside it. You have to just kind of, you got to figure out how to get all the work that you need done by your code done within a fixed amount of time. Okay, so those are the 2 big functions we were going to be spending most of our time with: prepare to play and then process block. Now, let's take a look at what happens over there. So in prepare to play, use this as the place to do any pre-playback initialization that you need. And then in process block, this is where you get your actual block of audio data. And if you're using a MIDI controller, these are where the MIDI messages are. But basically, this is where we do all of the work. We're going to be typing a bunch of code here, and we have to make sure that it doesn't happen in like more time than we have been allotted. Okay, let's go take a look at Plugin Editor. Now, Plugin Editor is where we set up all of our visual elements, and there's some basic stuff. You got your basic constructor, you got your paint function, your resized function. Painting, you know, it's what we're going to see. Right now we're showing a hello world. If I run this real quick. So before I get into showing how to run it, yeah, right now we're just going to see a hello world displayed at the center of the screen. And then if we have any child components like buttons or sub components or anything like that, we'll lay them out here in the resized function. Okay, so that's a basic overview. We're going to be basically making child components to represent the knobs and the sliders and the spectrum analyzer and the response curve, and then we're going to be, you know, drawing them in there based on some, you know, audio parameters that we've got. Okay, so let's run this for the first time. What we need to do is go to our particular scheme. We have a few targets. We've got a VST3 format. We have an audio unit format if we are on OS X, and then we have the standalone version. Okay. So I'm going to put this on standalone. In Visual Studio, you'll do something similar. You will set the target to run to be the standalone version. And then all we need to do is just run it. Build and run. It's going to compile these 4 files. It's going to compile any module files that are being used. All right, here's our standard plugin. It's not doing anything. It's just displaying hello world, but it is processing audio. So yeah, that's it. There's our basic plugin. We're going to turn this into the thing I showed at the very beginning. I wanted to add a quick note right before we get started writing actual code. What you need to do is go to Producer, click on this gear right now for the project, click on this gear, scroll down, and you need to change the language type to be C++ 17. Okay, a lot of the stuff we're going to be using this involves C++ 17. Okay, once you've done that, just click Save and open an IDE. All right, let's start coding. Navigate to the audio, to the plugin processor.h file, because we need to declare some variables. Audio plugins depend on parameters to control the various parts of the DSP. Juice uses an object called the audio processor value tree state to coordinate syncing these parameters with the knobs on the GUI and the variables in the DSP. So we need one of these in our audio processor, and it needs to be public so the GUI can attach all of its knobs and sliders and buttons and combo boxes and stuff to it. All right, so let's declare one of those. All right, we need to give it a name. I'm just going to call it APVTS. And then we need to make sure that we use curly braces here, not parentheses when we declare it. All right, the audio processor to connect to is going to be this audio processor. We are not going to use an undo manager. We're going to just call it parameters. And then we need to provide a function here to give us a parameter layout. So the APVTS expects us to provide the list of all parameters when it is created. So we need a function that will provide that for us in the form of an APVTS parameter layout. So let's create that now. All right, and we can just call it. And actually, let's make it static, since it doesn't use any member variables. I have an extra colon. Okay. Let's declare this guy right here. Now for this project, we will keep the DSP and the GUI simple. We are only going to have 3 equalizer bands: low cut, high cut, and peak. For the low cut and high cut bands, we will be able to control the frequency cutoff as well as the slope of the cutoff. For the peak or parametric band, we will be able to control the center frequency, the gain, and the quality, meaning how narrow or how wide the peak is. All right, so we will start with the low cut and high cut frequency parameters. And Juice has an audio processor parameter class. And let me pull up the documentation for this real quick, actually. All right, so Juice has an audio processor parameter class. This class is a generic interface towards all the different audio parameter formats that different plugin hosts use. For example, audio unit on OS X is used by apps like Logic or Final Cut or GarageBand. VST3 on Windows and OS X is used in apps like Cubase or Ableton Live, Reaper, or Bitwig. And then there's AAX for Pro Tools. Okay, now the audio processor parameter class has several derived types that represent things like sliders and switches and combo boxes. And for our needs, the audio parameter float type is used to represent parameters that should be represented on the GUI with a slider of some kind. So we want our frequency range to be adjustable over a wide range, so we are going to use an audio parameter float for this. So let's declare one of these. And I hope the font is big enough for you to be able to see what's going on. We're going to return our layout. And now we can add an audio parameter float to this. So layout dot, let's see, add. And these things want unique pointers, so we'll use make unique for this. Make unique. And we want a juice audio parameter float. We want that guy. All right, the name of this is going to be low cut freak. The parameter name will also be low cut freak. The normalizable range is the next part. Now the human ear has a range of roughly, it can pick up sounds from 20 hertz to 20,000 hertz. So that will define the range for our parameter. Let's create one of these. Whoops. Normalizable range. Where's the one that takes parameters? This is the one that we want. Okay. We're going to make it use type float. Okay, now the range start is going to be 20, and the range end is going to be 20,000. Now the interval value, we're going to use a interval value of 1, and what that means is that our slider will change the parameter's value in steps of 1. We could use bigger steps if we wanted to. For example, we could drag the slider. If this was set to 10, then our slider would go from like 20 to 30 to 40 to 50 every time we dragged it. But as we get in the upper range of frequencies, that could be helpful. But in this lower range, the audible effects of like 20 hertz versus 25 hertz, like they sound like different notes on the piano, whereas 2000 to 2050 does not really sound like different notes on a piano. So we're going to keep this at a step size of 1. Okay, the skew factor. Now the skew parameter lets us change how the slider responds. What that means is that we can skew the slider such that the majority of our mouse movements are covering the lower part of this parameter's range. For example, I'm reading my notes over here. For example, I could set this skew value such that 75% of the slider's range covers the values 20 hertz through 1000 hertz, leaving the last 25% of the slider's range to cover the remaining frequencies, 1001 hertz to 20,000 hertz. Or I could skew it differently so that the slider's bottom 10% covers from 20 hertz to 1000 hertz, and the remaining 90% of the slider's range covers 1001 hertz to 20,000 hertz. And since I don't want to be doing any skewing right now, I'm going to leave this set to 1. All right, and then the last thing is that the default value for this parameter. Now this is the low cut parameter, so we will give it a default value of 20 hertz. Because that's the bottom of the hearing range, and we don't want to hear this parameter do anything unless we actually move it. All right, so that takes care of the low cut parameter. Let me hide this plugin processor and just show the plugin thing, so you can see the full name of this guy right here. All right, we've got our name, we've got our parameter name, and then we got our normalizable range right here, and this is our default value. We are going to do the same thing with the high cut frequency. The only difference will be that we will set the default value to 20,000 hertz because it's at the top of the human hearing range, and we don't want to hear this parameter do anything unless we decide to change the value. So I'm just going to copy this. I'm going to change the name to high cut, and then this needs to be 20,000. Now let's do the same thing for the peak frequency. We will use the same range of 20 hertz to 20,000 hertz. The same step size of 1 and the same skew value of 1. The only difference is we will set the center frequency to a default of 750 hertz. And let's change the name to peak. For the peak gain, we will be expressing this parameter in decibels. And a good range of values to use here is -24 to +24. A step size of 0.5 means that when we drag the slider back and forth, it will represent a change of half of a decibel. And we want this slider to behave in a linear fashion, so we will use a skew of 1. And we don't want this to, by default, add any sort of gain or cut, so we're going to use a default value of 0. So I'm going to copy this. We're going to change the name to peak gain. The range is going to be -24.f with a max of 24.f. Our step size, 0.5f. Our skew of 1, and our default value of 0.0f. Okay, that's our gain. Next, the peak band's quality control. The quality controls how tight or how wide the peak band is. This is kind of an abstract number and it doesn't have any units. You can have a pretty narrow Q, which is reflected by having a high Q value, or you can have a very wide Q, which is reflected by having a very low Q value. So let's give ourselves a low value of 0.1 and a high value of 10. Well, I'm going to copy this. Let's copy this parameter. Change this to quality. Change that to quality. So we will, so we're going to give it a low value of 0.1 and a high value of 10. I'm going to use a step size of 0.05, which means when we drag the slider, it's going to go 0.1, 0.15, 0.2. These can be pretty granular sizes, which means we can have a lot of control, which is good. And always we want a linear response, so we will set the skew on this to 1. And on top of it, we want to use a generic default value of 1 for the Q, 1.f. All right, for the low cut and high cut filters, I want to have the ability to change the steepness of the filter cut. So I will give myself some 4 different options. Okay, our cut filters are normally expressed in decibels per octaves, or their responses are normally expressed in decibels per octaves. Sorry, the way the math behind the filter equations works ends up expressing these choices in multiples of 6 or 12. So that means we can have choices like 12 decibels per octave, 24, 36. So for this project, we're going to stick with 4 choices, 12, 24, 36, 48. So because we are using specific choices and not a range of values like with these sliders, this means we get to use the audio parameter choice object. So I'll show you what that's like. Audio parameter choice. So that's this thing right here. This thing, it needs a string array that represents the choices. And because both the low cut and high cut will use the same set of choices, I only need to create this string array once. So we're going to do that first. Let me get rid of this line. Let me scroll up. Okay, so let's make our string array. And now we're going to do 4 choices. And now we are going to construct something that says 12 dB per oct or 24. And we can do that like this. All right, that should make a lot of sense. Default value is 0. So we've got, i's first value is 0. So we've got 12 plus 0, then 12 plus 12, 12 plus 24, 12 plus 36. That gives us 12, 24, 36, 48. And then we're just sticking dB per octave on the end of that string. All right, now we just need to create the audio parameter choice and give it the string array of choices and use the default value of 0, meaning the filter will have a default slope of 12 dB per octave. Let's create that now. This is going to be called low cut slope. Choice is going to be our string array. And our default index will be 0. All right, and we just need to duplicate this line for the high cut as well. All right, now we have got our parameters set up in our parameter layout, so we can just return it and pass it to the audio processor tree value state constructor, which we have already done. We already did that right here. All right, now if we run the app as it is right now, we are not going to see anything other than that hello world. And that's because we haven't added anything to our GUI. But if I go up to the create editor function, we can use the generic audio processor editor to see what our parameters look like. So let's do that. We're going to comment that line out. We're going to write return new generic audio processor editor, and it's going to be this. Okay, so if we run it and take a look, first of all, make sure you are in standalone mode. If we run it, we are going to see some good stuff. Okay, if we look at our combo boxes, we can see that our slope controls show up this way. Here's our 12, 24, 36, and 48. Peak control, default value of 1, we can see it goes, 0.1, 1.5, 2.5, all the way up to 10. And then for our gain, we got 24. We can see that it's stepping by half of a decibel every time. Okay, so next we will work on the signal processing side of things. That's the next step, to make all these parameters actually do something. All right, we've got some parameters set up now. This would be a good time to make a commit and, commit what we've done. So that way, if what we do in the next step gets messed up, we can always revert back to here and try again. So added parameters, we can see what we did. We created the audio processor value tree state, created the parameter layout. Then we added our parameters and made it give us the generic audio processor editor whenever we go to look at stuff. And then we also changed the language to C++ 17 and did an export for, in my case, OS X. In your case, it's probably for, perhaps it's OS X or Windows. Anyway, we'll add those things, stage those, and make a commit. All right, so next thing we're going to do is add some DSP. Now, before we do that, before we actually start writing DSP code, we need to add the DSP module. So go to Producer, click on the modules thing right here, then click the plus button, and you're going to do add a module, global juice paths, and go to juice DSP. All right, once that is in there, then we can click on this guy. And now we have access to all of the juice DSP modules. Okay, I'm going to switch back to the single view for right now. So let me hide this and then go back to pluginprocessor.h. Back to my script. If you have never written any audio software before or used any type of audio software, then you might not be familiar with the concept of audio channels and stereo versus mono audio. So stereo means there's two channels, mono means there's only one. Now, each of the signal processing classes in the DSP namespace is set up to process mono audio, unless it's declared as stereo in the documentation. So what that means is that it's only going to process a single channel of audio. And since this plugin is going to be processing stereo audio, we need to duplicate all of the stuff we are going to use. And the DSP namespace uses a lot of template metaprogramming and nested namespaces. So let's help ourselves out. Let's create some type aliases to eliminate a lot of those namespace and template definitions. First thing we are going to create is a filter alias. We're going to be processing floats and not doubles in this project. That's our first alias. Now, I said before how we can set the slope of our cut filters to be multiples of 12. Each of the filter types in the IIR filter class has a response of 12 dB per octave when it is configured as a low pass or high pass filter. So if we want to have a chain with a response of 48 decibels per octave, we are going to need 4 of those filters. Now, a central concept of the DSP namespace in the Juice framework is to define a chain and then pass in a processing context. That's an important term. Pass in a processing context which will run through each element of the chain automatically. So we can put 4 of these filters in a processor chain, which will allow us to pass it a single context and have it process all of the audio automatically. So let's do that. Using cut filter equals processor chain. And then this is where we do 1 filter, 2 filter, 3 filter, 4 filter. As I mentioned earlier, if you configure the filter as low pass or high pass, it will have a 12 dB per octave slope. We can also configure that filter to work as a peak filter or shelf or notch or band pass or all pass. There's a couple other types. This means we can use one of these filters to represent the parametric filter. So now that we have the peak filter and the cut filters represented as aliases, we can define a chain to represent the whole mono signal path. So we'll do that using mono chain equals juice DSP processor chain. And then we will do a cut filter, then a normal filter, and then a cut filter. Now we need 2 instances of this mono chain if we want to do stereo processing, and to have access to the filter instances in order to adjust their cutoff, gain, quality, or slope. So let's declare that now. Mono chain. We got the left channel and the right channel. Cool. Now before we can use our filter chains, we need to prepare them. So let's go over to our prepare to play and do that. We must prepare our filters before we use them, and we do this by passing a process spec object to the chains, which will then pass it to each link in the chain. So let's declare one of those. And it needs to know the maximum number of samples that it will process at one time. It needs to know the number of channels. Mono chains can only handle 1 channel of audio. And it needs to know the sample rate. Now we can pass it to each chain and they will be prepared and ready for processing. And let's just make sure everything's cool and build it. Build succeeded. Okay, step number 3. This requires us to jump down to our process block. Now the processor chain requires a processing context to be passed to it in order to run the audio through the links in the chain. In order to make a processing context, we need to supply it with an audio block instance. Now the process block function is called by the host, and it is given a buffer which can have any number of channels. So we need to extract the left channel and the right channel from this buffer. And the left and right channels are typically channels 0 and 1 respectively. So the first thing we have to do is create an audio block which wraps this buffer. So let's do that first. We're going to get rid of this stuff right here. All right, this is a block and it is initialized with our buffer. Now we can use the helper function in the audio block class to extract individual channels from the buffer, which will then be wrapped inside more audio blocks. So we can do auto left block equals block.get single channel block. We want channel 0. Do the same thing for the right channel. Now that we have audio blocks representing each individual channel, we can create processing contexts that wrap each individual audio block for the channels. Process context replacing, it's a float. We're going to call it the left context. It's going to be initialized with the left block. Make another one. All right, so we have our block representing an individual channel. We have a context that kind of provides a wrapper around that block that the chain can use. Now we can pass these contexts to our mono filter chains. Left chain dot process, and we want the left context, and then right chain dot process, right context. Now if we run it, it will work, but we will not hear our filters do anything because we have not set up their coefficients. So this is going to be a good time to set up the audio plugin host so we can feed some actual audio through our plugin and show that the filters are not doing anything. But until then, we can actually just run this and you'll see that it's not going to do anything. Cool. So we can drag all this stuff. There's no audio running through it, so we're not going to hear it do anything. Okay, let's get set up with audio plugin host. This comes with Juice. Navigate to your Juice folder and then go to Extras and now go to Audio Plugin Host. And now open the, you can open the Juicer file if you want. I'll do that. Now I've got this here. It's just like the other thing where we have all our source and our modules and whatnot. So all we're going to do is just save and open in IDE. Wait for this to open. And now we just need to build it. All right, build succeeded. So we are done with this project now. That was very easy. Okay, what we have to do now is run it outside of our project. So go to the builds folder, go to your particular operating system. I'm going to go to Mac OS. Go to build, debug, and now run it. All right. It's going to want access to whatever device you have. What we have to do now is scan our system for the plugin. I haven't built it yet. I've only built the standalone version. So I'm going to change this to all, and I'm going to build it now. And what it's going to do is it's going to create a VST3. It's going to create an audio unit, and it's going to copy them to the relevant locations on the computer. Now I can go back to Audio Plugin Host, and now I can go to the Options menu and edit the list of available plugins. And now under this Options button here, this is where you're going to scan for both, if you're on Mac, Audio Unit and VST3. So we'll do VST3 first. It's going to find our SimpleEQ because we built it that way. And then for Audio Unit, do the same thing. In my case, I have a bunch of UAD stuff, so it's going to find all of that. Okay, so now that we have all of our audio units that are built into the computer and our VST3, close this available plugins list window. Now we can right-click right here, go to the your company, unless you put something else in, and pick VST3 for right now. Here's our plugin. So that's good times. Now we want to run some audio through it. So what we want to do is right-click here. On OS X, you're going to go to the Apple menu. You're going to go to the AU audio file player. Now this little plugin lets us load files and play them. We can load sound files and then play them. So we're going to wire this up, connect it to our audio output, and then be able to hear audio running through our plugin. So just drag like this and drag that to our audio output. And then, the other thing to do is you need to make sure that under your options, go to your audio device settings. And this is where you're going to configure your audio on what you have. Now I'm going to set this up with an audio file that I have. Feel free to set it up with your own. I'm just pulling something that I got from YouTube's free audio library, so that way this video doesn't cause any sort of copyright issues or anything. Set it up with whatever you have, and then I'm also going to configure it so that it plays through, so that the audio that I play shows up in the video instead of just going out of the audio output. All right, so stand by for that. Okay, I've got my AU audio file player set up with a file that is not going to trigger a copyright flag with YouTube. I've got it wired up to the SimpleEQ that we've been working on, and it's connected to the audio output. So if I push play, I'm going to hear it through the speakers, and you guys are going to hear it through this video. So check it out. All right, cool. So obviously this stuff is not going to do anything if I adjust that. All right, so that's the next thing we are going to work on. We need to set this as what opens by default when we run our application, so we will do that next. A good thing to do once you get this set up is save the setting, save the filter graph setting. I'm going to save it with my project. That's a good place to put it. Programming, put it right here, and just call it SimpleEQ filter graph. Okay, so now I can save that. Now I can quit this, and now I can configure the audio, configure my project to run Audio Plugin Host when ever I run the project. So I'm going to do that with a VST3. Go here for OS X. You're going to go here. You're going to go to Edits the Scheme, and you're going to configure the executable. So do Other. And then just search for Audio Plugin Host. And there it is. Choose. Close. And now if we run it, it's going to run Audio Plugin Host. And it should load our saved file. There it is. Okay. So now we can, now what we can do is actually debug our stuff. So if we add a breakpoint right here, it's going to pause execution right on that, which is cool. So now we can actually debug our code and whatnot while it's running in there. Okay, so we are done with Audio Plugin Host for right now. Okay, we are going to connect some parameters to our filters. But before we do that, let's make a commit and just, jot down what we did. So we went through this and we initialized our chains and we got our chains up and running. Basically, you could say we added our DSP, added DSP. Right? So here's where we created our chains. Here is where we initialized our chains. Here is where we started running audio through our chains. And then this is where we did, this is where we set up our filter graph. And then here is where we added the DSP module. Okay, with that out of the way, now we can start configuring our filter chain. So go to the plugin processor.h, and we're going to go up to the top. Now let's start by extracting our parameters from the audio processor value tree state. And a data structure representing all of the parameter values will keep our code nice and readable. So let's do that first. And now next, let's write a helper function that will give us all of these parameter values in our little data struct. All right, let's go to our CPP file. Now I'm going to implement this near where I created the parameter layout so it's easy to see the names. So I'm going to put that right above this. We'll just add this here, chain settings. Okay, now there are two ways to get parameter values from the APVTS. The first way is to call getParameter and then get value like this, VTS, get parameter, some parameter name like low cut freak, and then get value. But the problem with that approach is that we are given a normalized value. All of the functions that produce coefficients for our filter expect real world values, not normalized values. So we're not going to use this one. What we can use is a different function. We can use apvts.getRawParameterValue. Now this function returns the parameter in units that we care about. Units based on the ranges that we set up when we defined the parameters. So for instance, for the low cut frequency, it's going to return a unit that's within this range instead of a normalized value between these two values. So let's initialize all of our data structures, all of the properties in our data structure using this function. These raw parameter values are atomic, which is handy when we are interacting with the GUI later. I'm not going to talk about any of the thread safety issues that come along with audio development in this particular course. But you can learn all about that stuff in my course, which teaches how to build the full channel equalizer, and in several talks on YouTube from the Audio Developer Conference. All right, so let's go through these and start setting up our settings. Okay, there's all the parameters. Getting them all: low cut freak, high cut freak, peak gain. Making sure we're using all the names that we used here. Let's go up to our prepare to play function. All right, we're going to do this after we've prepared our chain. Now that we have our settings, we can start producing coefficients using the static helper functions that are part of the IIR coefficients class. So we can do this auto chain. Now we can do auto peak coefficients equals make peak filter. Now we need the sample rate and our center frequency, which is going to be chain settings. Oops, chain settings dot peak freak, chain settings dot q peak quality, and then for the gain parameter, this particular parameter expects a value in gain units, not decibels, so we must convert our decibel value to gain. Thankfully, there is a handy helper function to do just that. So that's juice, the decibels class, and then this function. And we feed it chain settings dot peak gain in decibels. All right, let's put all that stuff on its own line so it's easy to look at. Now that we have our coefficients for the peak filter, we can set our filter's coefficients accordingly. Now you can access links in the processor chain via a get function like this, left chain.get, and it's templated. This function wants an index to a particular element in the chain, via its template argument. So let's help ourselves out and define an enum that represents each link's position in the chain and use it here. All right, so we're just going to leave that the way it is. Let's go back to our header file. And we'll go down here to where our chain is, and let's define an enum here, enum chain positions. And we're going to have low cut, peak, and high cut. And this goes along with what we have here. We have a low cut, the peak band, and then the cut right here. We could change this to parametric if we wanted. Okay, now that we have that, let's go back to our CPP file, go back to prepare to play. All right, let's use it to access our peak filter link and assign some coefficients. So we're going to go chain positions peak like that. All right, that's how we get that particular filter link. All right, now the coefficients object, this thing right here, is basically a reference counted wrapper around an array that is allocated on the heap. Now we want to copy its values over, so we need to dereference it. And don't ask me why the juice people decided to design their coefficients object this way. Allocating on the heap in an audio callback is bad, but we're going to ignore that design flaw for right now and just keep moving forward. All right, so we are going to access the coefficients, and we're going to assign it across, peak coefficients, like that. And now we just need to dereference them. Right? And then we'll do the same thing with the right chain. Okay, at this point, our peak filter has been set up and will make audible changes to the audio running through it if the gain parameter is not 0. However, any changes we make to these sliders will not cause audible changes because we are not updating the filter with new coefficients whenever the slider changes. So let's do that next in our process block. So let's go down to our process block. And we need to do this before we run audio through it. Always update your parameters before you process audio through them. Okay, so let's just copy the code we created in prepare to play, right, where we created our coefficients. We can refactor this later. Let's just copy that for now. Go to process block. Put this right after this buffer clear stuff happens. After that, put it right here. Okay, again, we can refactor this later, even though it's identical. The only thing we need to change is this guy. Let's fix this so we can just call get sample rate. All right, and now if we run it and adjust the gain, Q, and frequency sliders, we will hear some audible changes. Okay, I have run it, and let's see what it gets. See what it gets us. Okay, we're just going to mess around with the peak frequency stuff. Okay. All right, it did something. Cool. So you might notice that the filter slider is kind of wonky. That's because our ears hear frequencies. That's because of how our ears hear versus how frequencies work. If the sound goes up 1 octave, the frequency doubles. So this is an instance of where we want to change the skew parameter of our frequency slider. Let's play around with some different values until we find something we like. So we go down to where our parameters are created. Let's see, which parameter was the skew parameter? I think it was, that's step size. Yeah, that's step size, so it's the last parameter. So I'm gonna just try 0.5 for the, let's see, I'm messing with the peak frequency, so we'll do that one first. Go like that. Let's rerun this, stop. I'm gonna change it to 0.5. Basically what it's gonna do is adjust how the filter responds when I drag the slider, okay? All right, now this is going to be more noticeable when you are messing with an actual graphical slider that you're designing versus these sliders here. So either way, I'm going to keep messing with this, and we'll see what value I end up arriving on. So something you might notice here is like the range is 20 to 20,000. If the slider's in the middle, you would think that a value of 0.5 would result in 10,000 hertz, but we don't actually see that until we're way over here. And this is what I was saying before about the skew thing. So I can based on this skew that I have right here of 0.25, the from 20 hertz to 10,000 hertz is spread out across this range, and then 10,000 to 20,000 fits here in this little range right here. So that's what the skew parameter lets us deal with. Okay, so something that I'm noticing when setting that skew really far down, like 0.15 or whatever, is I hit the bottom of the range here, and it doesn't go up to the next frequency until right there. So that's a big chunk of the slider that's not usable based on this skew value of 0.15. So I'm going to put this back to 0.25, and I'm going to use that for every other frequency parameter. Okay, so with that said, we added a little bit of code, so let's go ahead and make a commit. This is going to be, let's see, we connected the peak filter params to the filter. All right, let's go ahead and commit that stuff. All right, on to the next step. Okay, we are going to get the low-cut filters connected to the low-cut parameters. Now, if you remember, if we jump back over here, the cut filters were built with their own processor chain instance, and that instance has 4 filters within it. As I said before, each of these filters has a 12 dB per octave response if it is configured as a low-pass or high-pass filter. We are going to use a helper function from the Juice framework that allows us to define IIR filters with custom orders. And we've been describing the slope in terms of decibels per octave, but the slope of cut filters is also known as its order. Okay. Also, a low cut filter is also called a high pass filter, and likewise, a high cut filter is also called a low pass filter. So let's go take a look at the helper function we're going to use. Let's jump over to plugin processor, go to the end of prepare to play, and we're just going to call it so we can jump to the definition of it. All right, just give it some default parameters. It is the design IIR high pass high order Butterworth method. Okay, so just jump to the definition of that. That's going to take us to the declaration, but we want the actual implementation of this. Okay, if we take a quick look at the implementation, for example, this little loop right here, we'll do this loop because we're going to do even numbered orders. Okay, right here, if we look at the implementation, you will see that it creates one IIR filter coefficient object for every 2 orders. So if the order is 2, we are only going to get one of these. That's what I mean, how like this gives us a 12 dB per octave cut. If it's 4, if our order is 4, we're going to get 2 sets of coefficients. If our order is 6, we will get 3, etc., etc. So what we need to do is produce the required number of coefficient objects that are needed based on what our slope parameter is set to. Now remember, this parameter had 4 choices. It was 12, 24, 36, 48. Let me jump over to plugin processor and go down to where we created our parameters. I was down here. We had 4 choices total. All right, so the first choice is at index 0. If our choice is 12 dB per octave, which is index 0, we want to get back 1 coefficient object. And to do that, that means we need to supply an order of 2. Okay, if our choice is 24, like if we're doing I equals 1, we need to supply an order of 4 in order to get 2 coefficients back. Okay, ergo, our possible orders are then, as in I'm talking about this parameter right here, this parameter, our possible orders are 2, 4, 6, and 8. Okay, so we need to add 1 to our slope choice and then multiply that by 2 to get the order to use when calling this helper function. Okay, once we have done that, we can get our array of coefficients from this helper function. Okay, I'm going to say that one more time. Our possible orders are 2, 4, 6, 8. So remember, our slope choices are 0, 1, 2, 3. So what we have to do is add 1 to our slope choice and multiply that sum by 2 in order to get the correct order to pass to this function. Okay, Let's do that now. Go to plugin processor, go back up to the prepare to play function, and we're going to just get rid of this line. We're going to do auto cut coefficients equals, and now we're going to call that. All right, our frequency is going to be the chain settings low cut frequency, sample rate, and our order is going to be, remember, we're going to do our chain settings, our slope for the low cut. We're going to add 1 to it. We're going to multiply that value by 2. 2 times that. All right, let's put these all in their own line so it's easy to look at. Okay, chain settings. Remember, this is a value between 0, 1, 2, and 3. So we're going to add 1 to that. That's going to give us 1, 2, 3, 4, and then we're going to double it, which is going to give us 2, 4, 6, 8. Okay. Now we need to start. Let's start by initializing the left chain first. All right, so let's get the low cut filter chain. So we'll just do auto left low cut. We're going to get it. Chain position. Whoops. All right. Now, first we are going to bypass all of the links in the chain. All right, remember there are 4 positions, so we need to bypass all 4. All right. Now, it would be ideal to be able to switch based on the slope setting. So to make the code more readable, let's define another enum that represents our slope setting, since enums decay to integers, which is what our choice parameter is expressed in. Let's go to the top of our plugin processor.h. We're going to define an enum up here. So I want to have the slope amount in the enums member name, and since we can't use numbers to begin identifiers in C++, I'm going to put slope before that. So we will do enum slope, and I will do slope 12. All right, now let's adjust what the filter chain slopes are specified as. Let's change this guy right here. So instead of it being low cut slope expressed with an integer, let's express it with a slope. All right, we'll do the same thing for the high cut. Okay, now if we try to compile, we will get an error. Let's fix this error next. All right, what we have to do is change the data type right here to, we're just gonna cast this to that slope type right here. Do the same thing for this line. And try building it again. Cool, problem solved. All right, now we have our enum, which gives us specific types that we can switch on. Let's go back to our prepare to play function. Oops, all right, that's down here. Now we can do a switch statement. So switch, and we want to do chain settings, low cut slope. All right. I'm too lazy to type the switch types, so I'm going to let the autocomplete do it. All right, add missing switch cases. Yes. Okay, now we just need to fill them in. If our order is 2, meaning a 12 dB per octave slope, the helper function will return an array with 1 coefficient object only. So we will assign those coefficients to the first filter in the cut filter chain and also stop bypassing that filter chain. So we will do, let's see, left low cut dot get first filter in that chain. We want the coefficients, and we're going to assign it to our cut coefficients, the first element. Now remember, we have to dereference, and then we are going to stop bypassing this particular chain. All right. Now for the next choice, we will do the same thing that we did when the slope was 12. However, the helper function will return an array with 2 coefficient objects. So we will assign to the first 2 links in the filter chain and stop bypassing them. All right, I'm just going to copy this and then copy it again and change these to 1. All right, we're going to repeat for the third and fourth option when the slope is 36 and when the slope is 48. All right, now that's obviously not, optimized. There's a lot of repetition in the code going on. We'll deal with that later. Okay, all we have to do now is repeat this for the right chain, and our slider and combo box for the low cut filter will configure the filter properly. All right, so we are going to get the right chain, and let's just copy all of this and replace all of the left low cut with right low cut. Okay. All right, as I said, there is a lot of repetition here, and it could do with some refactoring, but let's not do that just yet, okay? First, let's copy this chunk of code to our process block, just like we did with the peak filter, and we should be able to run it and test the sliders and the combo box and hear it adjusting the low cut filter. All right, so just grab all of this, grab the cut coefficients, like that. Jump to process block. We're gonna put this after our peak coefficient stuff. Right, like that. Okay, the only difference is sample rate. We need to call get sample rate again. All right, let's run it. Okay, we should be able to adjust the low cut frequency as well as the low cut slope and hear it make a difference. All right, let's adjust the slope. So I'm going to put it around 2,500. Put it around 4,000. We can definitely hear there's more bottom end when we use a more gentle slope versus a steeper slope. All right, I'm happy with that. Okay, let's make a commit since we did some good work right there. We added the, we connected the low cut parameters to the filter. We made our enum. We adjusted our chain settings, how they are defined, and we added our coefficients, and we got them working with our working with the filter, and then we also updated how we pulled them from the process block or from the APVTS. All right, cool. On to the next thing. We will refactor what we are doing. Okay, let's start the refactor with cleaning up the stuff that configures the peak filter. Let's just do a function here at the bottom. All right, we're going to update the peak filter with the chain settings. I'm going to implement this beneath where I am getting the chain settings. Now I'm going to just copy the implementation from the process block, paste it here, replace it in the process block, and then do the same thing in prepare to play. Just going to copy this stuff, paste it here. And now I'm going to call this. I'm going to do the same thing in prepare to play. Very easy. Now let's add a helper function since we will be updating lots of coefficients. Like we are updating them here, we're updating them here, 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 here. Okay, so let's go back to our header file and let's do that here. Now, I'm not sure of the exact type that the DSP IIR filter class uses for its coefficients. Take a look over here. It uses this thing, which is an alias to whatever this is. But we can make an alias to that alias very easily. And now it's very easy to declare this helper function that will update those coefficients. Now it doesn't use any member variables, so it could be a free function or it could be a static member variable, static member function. So I'm going to go with static for this particular instance because I'm already right here. I don't want to have to scroll up to make a free function. All right, and let's go implement that below where we implemented our update peak code. Okay, remember they're reference counted objects allocated on the heap, so we need to dereference them to get the underlying object. Now we can use it here. The old ones are going to be this thing. The replacements are going to be this thing. We'll do the same thing for the right chain. Okay, let's run this and then move the sliders, make sure it works. And if it's cool, then we'll delete this old code and then do the low cut filter next. Okay, so we're just going to mess with the peak filter. All right, it's making changes. Make it tight. Give it a little sweepy peak. Cool. All right, let's clean this up and then commit our changes. Let's build just to make sure that what we deleted is cool. All right, let's make a commit. All right, here we go. Commit that, stage all this stuff. Boom. Okay, we can refactor how the low cut filter gets configured next, and then we can use that same code to configure the high cut filter. Let's refactor how the low cut filter is updated. So we'll be able to use this later for the high cut filter. Now, I'm not sure what type names to use for the parameters here. So I'm going to use a templated function. So let's go to our header file and put this down here. Template type name, chain type, and then void update cut filter. Now a trick when refactoring something like this is to use the same names you were using in the unrefactored code. So I'm going to use, if we go take a look at our plugin processor, I'm going to use the same names here where I've got cut coefficients and then left low cut and then low cut slope. I'm going to use those same names for right now. Okay, so we're going to do a chain type of left low cut. I'm going to use a coefficients type of cut coefficients. And then I've got my chain settings, const chain settings, chain settings. All right, so let's copy over the stuff from process block first and call it in process block and then comment out the old stuff. And we will fix any errors along the way. So let's go to our plugin processor. We're gonna grab this cut coefficient stuff and then all of this code right here. And now let's comment it out and call our function. All right, we want to call it with our left low cut. Let me call this after this point, so I still need this thing. All right, so let's see. I still need my cut coefficients too. Update cut filter, we're going to call it with left low cut. We're going to call it with cut coefficients and our chain settings. Let's give that a quick build just to make sure that that works as expected. All right, we have some errors going on here. Ah, yes. Okay, so we're not passing this and we're not passing that. So comment that out, and that should be good to go. All right, so we need to add some template keywords right here. Template. And that also needs to go here in front of these, since these are template functions. We have to explicitly declare that they are templated like this. It's one of the more obscure C++ rules. All right. Okay, cool. Build succeeded. All right, the left cut filter is configured, so we can tackle the right cut filter with our helper function now. So we just do this same thing. Comment out all of this code, call our helper function, and use the right low cut. All right, we'll do a quick build just to make sure. Build succeeded. All right, cool. Now we aren't using the entire chain settings object. We're only using the slope. So let's go back and change our switch statement. Okay, we're going to get rid of this, and we're going to change our parameter. So we're going to get rid of this. We're going to change this to be const slope, low cut slope. And now we can change this line to be switch low cut slope. Let's build it. We should get some errors because we need to change what we're calling it with. This is where we need to do low cut slope, and then on the next one as well. All right, and if we build it, we should get no errors. Okay, cool, no errors. So let's revise prepare to play now. Let's go up here to prepare to play. And we need our coefficients, our left low cut, as well as our right low cut. So let's get rid of this code and this code. And now let's call, we'll get rid of that code too. And now we can call our code. We can call our function. All right, we'll start with the left low cut filter chain, update cut filter with the left low cut chain, and our cut coefficients and our left low cut. This is where we need our chain settings dot low cut slope, and then do the same thing for the high cut, or for the right low cut. Our slider and combo box for the low cut filter should configure the DSP filter properly. All right, let's test out our refactor, and if it's cool, we will delete all this code and do a commit. Okay, let's run it and see what we get. Okay, so we are going to mess with the low cut now and the slope. That's working. All right, I am very happy with that. Let's clean this up and make a commit. All right, let's clean up our header file. Okay, let's build it just to make sure. All right, looking good. Updated or refactored low cut configuration. Low cut filter configuration. All right, this is where we added our helper function. This is where we deleted our helper, our old code, and now call the updated stuff. Now, this is obviously very verbose, so let's clean this up. We're going to use a special trick. Just comment all of this out. If we reverse the switch order, we can leverage case pass through to eliminate a ton of code duplication here. So I'm going to do that first. All right, we're just going to put the cases in the opposite order. Case slope. Okay. The way this works is like if it's the 48th, if our slope is 48, we want it to do this one. And then we also want it to do all of these. So we can just make it, instead of making it break out of the switch, we can just do, okay, if it's 48, do this, do that one here. And then also do the one that is required for 36. We can also write a templated helper function to eliminate even more duplicated code because we're doing this thing. And yeah, all right, so let's write that next right above this guy. All right, so we're gonna do template. We'll add these parameters next, void update. So we're gonna need our chain. We're going to need the coefficients. And then, so we're going to need our chain type and our coefficients. And then if you notice, all of these make use of this get or set bypass, and it uses a parameter here. So we are going to make this be the first parameter, because if you didn't notice, when we called this function, we didn't have to provide any of these template arguments. So the compiler deduced what to put here automatically. So if we leave these as the later template arguments, the compiler can deduce them for us, and we only need to provide that index. So we're going to do that, int index. Okay. Now we can just do that update coefficients function, update coefficients, and our old one is going to be chain dot this thing right here, template get dot coefficients. All right, and our coefficient replacement type is going to be the coefficients, cut coefficients. Is that the name I'm using there? I'm going to change that name to just coefficients. And the index that we use, if you notice, it's always when it's get 0, we always use the 0th cut coefficient index. When it's 1, we use the index 1. Okay, so whatever we put here, our index is the same thing we're going to use here. Index. All right, how convenient is that? And then we need to set the bypass state to false. So we can call that chain.template set bypassed index false. Cool. All right, now we just need to call it. All right, so remember, if we're doing the 48-degree slope, we want to call this. All right, and this is being replaced by that update function. This is where we want index 3, and our chain type is left low cut, and our coefficient type is the cut coefficients. Let me spell that right. All right, that gets rid of these lines. All right, we do the same thing, 3, 2, 1, 0. 3, 2, 1, 0, 0. Okay. Let's test that out, make sure that works. If it does, then we can clean this up. All right, so we're going to run it. We're going to adjust this and adjust this. All right, that's filtering. Let's put this on 48. Put this to 5,000. All right, and we'll change the slope. And we hear more bottom end material. Not much more, but. All right, cool. Awesome. Let's make a commit of that after we clean it up. All right, cool. Is there anything in here that needs cleaning up? I don't think there is. Prepare to play. Nope. All right. Let's make a commit of that. So refactored chain update. Refactored update cut filter code. All right, cool. Get some more advanced C++ stuff going on with that. All right, now we can connect the high cut parameters to the filters. All right, so let's go over to our plugin processor.cpp and go up to the prepare to play function first of all. Now we need to let's see. Go back to my notes here. We need to rename our coefficients before we dig into high cut filter configuration. So let's change this to be low cut coefficients. All right, now that we've done that, now we can configure the high cut chain. We're going to follow the same pattern. We're going to call the helper function to get coefficients, and then we're going to call the helper function to update the filters with those coefficients. Okay, so we're going to do auto high cut coefficients equals juice. Okay, we want the design low pass high order Butterworth method. All right, same thing. It's going to be the chain settings dot the high cut frequency, same sample rate, and then our order is going to be this same expression, but it's going to be the high cut slope. Okay, now we can get our left chain and right chain. Left high cut, high cut. Do left chain and right chain. Okay, and now we can just call this guy. Call it with left high cut and the high cut slope, and then do it again for the right side. And then we need to use our high cut coefficients. And then we will do the same thing. We can obviously refactor this later. We can do the same thing in our process block now. Process block, let's just put this at the end of our update filter code here. And then, we need our get sample rate. And now, now that this is in place, we can run it and test it. All right, so we're going to be testing the high cut frequency and the high cut slope. All right, so I'm going to set this around 2500 hertz. Now if I change the slope, I should hear less and less high frequency. Perfect. All right, cool. Let's do a don't repeat yourself refactor, and that'll wrap it up for the DSP side of things. That was easier than probably you thought. So the first thing we are going to do is go to our plugin processor.h. Down here, let's make a function that's going to update all the filters. Now we need a pair of functions, one for the low cut and one for the high cut, and these will be called by the by this update filters function. Okay, so void. All right, takes care of those. Let's go over to our plugin processor.cpp. I'm going to jump to after the updates coefficient function, update coefficients function. I'm going to copy the relevant code from process block to the implementation for the update low cut filter. Let me grab that from process block. All right, let's just copy that. Paste that here, make sure we're getting the coefficients and then updating both chains. We're going to do the same thing for the high cut. Void SimpleEQ. Let's go grab that code from the process block. High cut coefficients, update cut filter. All right, now we need to implement our update filter function. So I'm going to do that below this. Now I just need to get the chain settings. Auto chain settings equals get chain settings. Now I can call update low cut filters, update peak filter, update high cut filter. Now we just need to replace all of that stuff in process block with a call to that update filters function. right, we don't need our chain settings anymore. We don't need any of this. Update filters. Okay, let's do the same thing in prepare to play. All right, we lose all of this code, which is great. All right, let's run it just to make sure. All right, we're going to adjust all the sliders, and it should work as expected. All right, there's our low cut. All right, low cut's working. There's the high cut working. Let's get rid of some more high end. Okay, high cut's working. Let's mess with the peak. Cool. All right, that works. Let's clean this up. Delete that code. Go to our process block. Delete all this code. All right, let's see if there's anything else that's commented out. Nope, just those guys. Just those guys. Okay. DRY refactored DSP config. DSP filter configuration. All right, commit. Okay, cool. So that wraps it up for the DSP side of things. Okay, so that's awesome. All right, the next stuff we get to work on is the GUI side of things. We get to design a custom interface and knobs and get the response curve showing up and the FFT analysis showing up in the background as well. Okay, see you in the next one. Thanks for sticking with me to the end. Well, we learned how to make this simple three-band equalizer with FFT analyzer. If you liked what you experienced here, you can check out my course Project 11, where you will learn to build the Project 11 plugin from scratch. I also have a course that teaches C++ from scratch in the context of writing audio software. The focus there is on mentorship and not on video tutorials. Programming is learned by doing, not by watching. So for that, you're going to work your way through 10 projects. I'm going to review your code every step of the way via pull requests on GitHub and Bitbucket because that's what we use in the real world. 9 of them are pure C++ projects that will teach you the language fundamentals. The 10th project is a multimeter audio plugin written in Juice, just like we used here. It features level meters, histograms, goniometers, correlation meters, buttons and combo boxes, threshold sliders, saving and loading the plugin state, and a little bit of the DSP. Basically what you experienced here, but with way more visual stuff being built. And you aren't watching me build it either, okay? You are building it on your own. I take on the role of your project manager. I set up a Jira board with all of the instructions because that's how companies manage projects in the real world. I assign you issues from that board. You tackle them. I review your work and either help you when you get stuck or I approve it and assign you something new. In the end, you'll have built the whole plugin from scratch without me writing a single line of code for you. You're going to do it all yourself. I'm just there when you need help. So it's a pretty cool experience. I've had a lot of people go through it. I've had a few people actually manage to land jobs at some pretty big audio companies. So check out the link in the description or by visiting www.programmingformusicians.com. Thank you again for tuning in. I am Chuck. I also go by the name Madcat Music on Instagram and YouTube. Good luck on your coding journeys, and I will see you in the next project.